Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a final video in an introduction to definite integrals for a differential calculus course, or a beginning integral calculus course. And this is more of a best practice video, kind of ideas that you should keep in mind as you move through your math courses, specifically calculus and integral calculus. You should always keep in mind, the best practice is always keep in mind the definite integral is the signed area under a curve. This will allow you to sometimes use algebra or geometry instead of calculus. So let's take a look at this. Use properties of integrals to verify the inequality without evaluating the integral. So we want to use properties of, we just want to verify this inequality basically. Well, one way you could do that, they're saying that the value of this integral, whatever number it becomes, is greater than or equal to 0. The best way to do that is just to quickly graph out the function. F of x is equal to x minus 2 quantity squared, because that's really what that function is. And if you graph that out, here's 2. From 0 to 4, it looks like this. And notice this is greater than or equal to 0 on all intervals really, but specifically on that interval. So since f is greater than or equal to 0, we have a property that says the integral from 0 to 4 of f of x dx must be greater than or equal to 0. That's it. So use a little bit of geometry, graph it. If your graph is always greater than or equal to 0, then the area underneath that curve is always positive. In fact, in this case, you can even say it's symmetric, right? So if you know this area right here, then you double it up, you get the actual area underneath the curve from 0 to 4. Unfortunately, we don't know the area right there, but if we did, then we could double it up and we'd have the full area. You want to use that style of thinking throughout calculus. Symmetry is your friend here. So let's see what else we have. This is kind of a review of something we did earlier, but let's go ahead and show this is true. So show that the integral from -1 to 1 of 1 over 1 plus x squared sits between 0 and 2. So the area underneath that curve is between 0 and 2. First of all, I would graph that curve. That curve's actually pretty easy to graph. When x is 0, the y value is 1, and then it tapers off after that. It actually looks something like this. It doesn't hit a y value of 0, but it gets close. And we're going from x equals -1 to x equals +1. And let's see, it's supposed to be symmetric. Sorry about that. Just do that. Even though I have a pen, I could easily erase that. I just didn't. But we want to showcase that the area underneath this curve is between 0 and 2, somewhere between 0 and 2. Well, that should be pretty darn easy, because this height here, that's x equals 0, y equals 1. And we know that if we were to create a big old box here, the area underneath that big old box is greater than the area underneath the function. So the area of the box, area of red, I'll just say it that way, is equal to height, which is 1, times width, which is 2. So I easily can say that will imply the area underneath the curve, which we had just graphed there, is definitely less than or equal to 2. And since the curve is positive, we know it's greater than or equal to 0. Again, because f is greater than or equal to 0. There you go. there's, you could actually tighten up this bound, by the way. So I could have technically even got it tighter to say, well, look, at 1 and -1, that height is 1/2. And so I could say, honestly, that the area underneath the curve is bigger than this black shaded area. Area of black, if I really wanted to do that, so area of black is equal to, again, when x is 1, our function is 1/2, or 1/2. So the height is 1/2. The width is still 2, so it's 1. So technically, I could tighten up that bound and tell you with absolute confidence that the area underneath that curve is between 1 and 2. But they only wanted me to showcase it's between 0 and 2, but I can tighten that up. It's between 1 and 2, honestly. Now, I mentioned something about symmetry. Symmetry is your friend. And here is a perfect example. Suppose that you're given an odd function, which is continuous, okay? So just graph any old odd function, like, for example, a sine curve. The sine is an odd function, so there you go. It's symmetric about the origin. If we were to try to find the area underneath that odd function from, let's say, a -a to a +a, let's take a look at this. From a -a, we have that negative area right there, and we have a positive area right here. Well, wouldn't you agree that the areas I've just highlighted are equal and opposite in value? In other words, that if that's area A, capital A, this is the opposite of that area. And when you add those areas up, they become 0. So that is actually the answer. So this becomes a really cool style of problem if I start giving you odd functions, like I need you to integrate from -pi to pi, x cubed minus the sine of x, plus the tangent, no, I don't want to do tangent, plus, I don't know, some other odd function, x times the absolute value of x dx. Each one of those functions is odd, so the entire function here is odd, which means it has this type of symmetry. And you're integrating over a symmetric interval from -pi to +pi. So the negative area will cancel with the positive area, and this will become 0. Very, very fast. Little geometry can move mountains here. So be very aware when you're working with an odd function. Use the fact that it's odd to your benefit. It speeds things up significantly. This piece of advice I give every semester, and then I still see students in Calc 2, in my Calc 2 classes, who will not take advantage of that, and they spend forever calculating things. And it's like, you do realize that was a definite integral with symmetric bounds from -pi to +pi or whatever of an odd function. And you spent 20 minutes trying to figure it out, and you got to an answer of 0. Like, you could have easily just said it was 0 because it's an odd function. So that's just a heads up. You should prove that it's an odd function, by the way. When I say prove, just say, well, f of -x is equal to, like in this case, -x being cubed minus sine of -x plus -x, absolute value of -x, is equal to a -x cubed plus the sine, because sine is odd, so you can bring out that negative, minus x times the absolute value of x, which is equal to the opposite of x cubed minus sine of x plus x, absolute value of x, which is equal to the opposite of f of x, right? So that showcases this is an odd function. Once you've done that, you've shown that that symmetric interval for that definite integral will become 0. So this goes back to what I've been saying all along throughout calculus. Arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. So basically exhaust all possibilities before you dip your toes into calculus. This is an incredibly popular problem. Again, if you're handed this and you don't know how to evaluate this, geometry is your friend, at least trigonometry. So if you graph the sine curve from 0 to 2 pi, you should probably agree with me. This area right here is a positive area. We'll call that area A. And this area right here is a negative area. And you should probably agree with this. It's the same area as that blue area. It's symmetric. So the area underneath the sine curve from 0 to 2 pi will be 0. Again, because it's symmetric. It's not symmetric from about an interval though. It's a periodic function. And so because it's periodic, the upper half always cancels with the lower half. Now, that is not the case if you're integrating from 0 to 3 pi over 2, right? You'd only go partway through, and that's a problem. So the fact that it's 2 pi periodic and we have a full 2 pi, they cancel. So that's why. That's a really, really good way to do your calculus without doing calculus. And finally, this guy right here. This was a style of problem that was given to me when I was a student in my integral calculus course. And it was on like an exam that is the second exam in Calc 2. And it involves trig subs and stuff like that. This could be a very complex problem if you don't think. But this was on the exam, and what I did was the following. I said, well, this piece right here, if you think about it, if you said y is equal to square root of 9 minus x squared, if you square both sides and then add x squared to both sides, you should realize that is a circle of radius 3. It's been lifted up 1 unit. Okay, so again, this is actually the top half because this is y equals the square root, and this is a positive square root, so it's the positive half of a circle. So top half of a circle of radius 3. You should all agree with that. And this is lifted 1 up. Okay, so now if I graph that picture, I have a circle of radius 3 lifted 1 unit up. That's what it looks like. That's my circle of radius 3. Here's x equals 3. Here's x equals negative 3. Now let's go back to the problem. I want to find the area underneath this curve from x equals negative 3 to 0. Again, the area underneath this curve, let me shade it in, from negative 3 to 0. Well, I could break that into 2 parts. A rectangle, that's the lift up by 1 unit, that's this part right here, and 1/4 of a circle. That's it. And that's how I did the problem, and I got 0 credit until I argued my points back, because I said, well, why would I do calculus when I can do algebra? And it was a very good point, right? Why would you do calculus when you could do algebra? All right, let's go ahead and figure out what this is. By the way, you didn't have to lift it up 1 unit. You could have done this. You could have said, oh, that's the integral from negative 3 to 0 of 1 dx, plus the integral from negative 3 to 0 of the square root of 9 minus x squared dx. A lot of people prefer that because when they do that, they go, oh, then I'm really dealing with these 2 curves. Y equals 1 from negative 3 to 0. Well, that's super easy, right? It's a 3 by 1 rectangle. So that's going to be 3 by 1. Plus the area underneath a circle from x equals negative 3 to 0, or in other words, this quarter circle. That's what this is. And we all know the area of a circle is pi r squared, but we're only taking a quarter of that circle. There you go. And so the answer to this problem is 3 plus 9/4 pi. That is the area underneath the original curve, 3 plus 9/4 pi, without using calculus, other than knowing what the symbols mean here, the definite integral. But this is what you need to do. You need to really be involved in understanding the geometric shapes you're working with. So this is why algebra and geometry and trig are so important as prerequisites. So once you are able to see something, you could say, oh wait, that's the top half of a circle. So I don't have to do calculus here. I could do algebra. That's what you want to be at. All right. That is a best practice, or that's one of my best practice videos for working with definite integrals.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.